Welcome to our channel. In this video, we share content for historical and educational purposes, presented in a way that draws you in and encourages you to see the past from a fresh perspective. Stay with us. Surprising facts and exciting discoveries await. It was January 5th, 1943, when Allied artillery suddenly became far more accurate and effective. The same equipment, almost overnight, began intercepting enemy aircraft with a level of precision never seen before. Soon, this upgraded capability also improved their ability to target opposing ground forces. This development, kept strictly confidential at the time, played a major role in shaping the outcome of the war. To understand how it happened, we need to go back to the basics. After learning difficult lessons from the First World War, where the majority of battlefield losses were linked to artillery, many countries still viewed artillery as the dominant force in land combat throughout the 1930s. Before the Second World War, most militaries focused on three long-established goals: counter-battery fire, interdiction, and infantry support. Counter-battery fire involved identifying and neutralizing the opposing artillery before it could strike. Interdiction meant aiming deep behind enemy lines to disrupt movements, supplies, and reinforcement efforts before they reached the front. And the third objective was direct support for friendly infantry, providing them with high-impact assistance exactly when and where it was needed. But early artillery technology had its limitations. Accuracy depended on approximate coordinates relayed to artillery teams, who then calculated trajectories by hand using paper maps, rulers, and angle boards. After firing an initial round, they waited for updates from a forward observer, communicating first through wired telephones and later through radio, who would report where the shells had actually landed. They would then make the necessary adjustments and continue refining their aim until the rounds aligned with the intended target. When the Second World War began, most nations were still using artillery tactics similar to those from the previous conflict, now enhanced with better communication tools and the gradual shift from horse-drawn to motorized equipment. Even with these upgrades, many armies still depended on large, concentrated fire missions and prolonged bombardments to weaken defensive positions. But within just a few years, several new inventions would dramatically reshape how artillery was used. At the start of the war, artillery units were divided into specialized branches. Field guns used a flatter trajectory and were primarily designed for direct fire. Howitzers launched heavier shells on a curved path, allowing them to strike targets that could not be seen from the ground. Mortars fired at steep angles and supported nearby infantry since they were lighter, faster to set up, and easier to move across the battlefield. There were also dedicated anti-air and anti-armor units, available in lighter and heavier configurations, with most equipment ranging from 20 mm to 155 mm. A few rare exceptions existed, such as extremely large railway-mounted guns with exceptional size and range. And yes, those massive weapons came from the countries known for producing advanced heavy engineering at the time, shared here in good humor and with respect to all viewers. For the most part, the core design and operation of artillery pieces remained consistent throughout the war. Calibers increased as technology advanced, and the need for more powerful munitions grew, but the fundamental principles behind how the guns worked stayed largely the same. The biggest changes during this period came from the types of shells being used, so let's break them down briefly. The most common were high-explosive rounds, followed by shrapnel, anti-armor, anti-aircraft, smoke, and illumination rounds, along with a small number of more specialized types, such as high-explosive anti-armor. Historical records also note that, in certain conflicts, some forces used harmful chemical-based munitions disguised as smoke rounds. These actions are widely condemned today, and are referenced here only for historical context. A key component of any shell was the fuse, the device attached to the front of the round that triggered the explosive charge inside. For safety, shells were transported without the fuses installed. Crews would attach and prepare them only shortly before firing. These fuses also included multiple safety features to ensure they would not activate unless actually launched, so accidental drops would not cause harm. High-explosive shells typically used point-detonating fuses, meaning they activated on impact, simple and straightforward. Another option was the mechanical time fuse, which could be set to detonate a certain number of seconds after the shell was fired, usually anywhere from 0 to around 30 seconds. Timed fuses were useful against fortified or hidden positions because a burst above the target could spread fragments more effectively than a ground impact, which often absorbed much of the force. However, using timed fuses accurately was extremely challenging. It required precise calculations to avoid the shell detonating too high in the air or striking the ground before activation, and achieving that precision in real battlefield conditions was far from easy. Even the smallest miscalculation, just a fraction of a second, could cause a timed shell to detonate too early or too late. The primary use of these timed fuses was in anti-aircraft roles, especially in systems such as the well-known German 88mm anti-air gun. Here's how it worked. A mechanical time fuse could be set manually with a tool, or, in the case of German crews, automatically through a built-in device called a fuse setter. The shell would be placed into this system, and the fuse would be adjusted to the exact timing needed before firing. So why rely on timed fuses when aiming at aircraft? Because early radar and targeting technology made it extremely difficult to hit fast, high-altitude planes directly, crews depended on visual tracking and basic range-finding tools, adjusting their aim after each volley. Actually striking an aircraft with a direct hit was incredibly challenging. Timed shells solved part of this problem by detonating at a planned height near the aircraft, rather than needing to strike it directly. When the shell burst, it released a wide spray of fragments designed to damage engines, wings, or other critical components of aircraft built with lightweight materials of the era. Those dark bursts you see in historical footage above bomber formations were these timed explosions. When dozens of aircraft flew together and hundreds of anti-aircraft guns fired in coordination, often guided by centralized fire control systems, there was a significantly higher chance of disrupting or disabling an incoming threat. German anti-aircraft units did manage to bring down many aircraft during the war, particularly against large bomber groups. However, each successful hit required an enormous amount of ammunition, often thousands of shells per aircraft, showing how the system depended heavily on sustained, high-volume fire rather than precision. At the time, the German approach was considered advanced because it combined searchlights and early radar to track incoming formations. This information allowed crews to estimate altitude, speed, and direction, helping them coordinate their fire more effectively. Anti-aircraft guns, often called Flak, a term derived from the German word for air defense, were usually arranged in groups of 4 to 8 and connected by cables to a central command post. At the command post, operators used a large mechanical calculating device that received real-time information on incoming aircraft. This device processed altitude, direction, and speed to assist with aiming. The results were then passed to each gun crew, who adjusted their equipment to match the provided settings. In many cases, the entire battery could even be coordinated to fire simultaneously. Because aircraft at high altitude could take around 20 seconds for a shell to reach, crews had to estimate where the aircraft would be by the time the round arrived, aiming not at its current position but at its predicted future location. In practice, even with detailed calculations, it still required significant amounts of ammunition before any rounds reached the correct point in the sky. Early on, Allied forces used similar anti-aircraft systems, though typically in smaller numbers. Germany relied heavily on these defenses due to frequent and sustained air raids during the strategic bombing campaigns. The situation shifted dramatically, however, once the United States and Britain entered large-scale naval battles in the Pacific. With aircraft carriers at the center of operations, and with fighter planes, dive bombers, and torpedo aircraft constantly involved, ships needed highly effective anti-aircraft protection. This became even more crucial later in the war, when certain Japanese aircraft carried out direct, high-risk attacks against ships. In this environment, a single successful strike from an aircraft carrying ordnance could significantly damage or even sink a vessel, making reliable ship-based air defense systems more important than ever. At the beginning of the conflict, many ships were equipped with 50-caliber machine guns, 20mm cannons, and 40mm anti-aircraft guns. Larger vessels also carried 5-inch dual-purpose naval guns that could be used against both sea and air targets. But as the air threat increased, it became clear that ships needed far stronger protection. The United States responded by significantly expanding ship-based air defenses. This included adding a large number of anti-aircraft guns and installing them in twin, triple, or even quadruple mounts to greatly increase firing speed and coverage. As a result, a single ship could release an enormous volume of defensive fire in a short period of time, creating a coordinated protective barrier around the fleet. Large vessels such as the Iowa-class battleships could carry up to 20 quad-mounted 40mm guns, plus many additional weapons designed for close-range defense. When multiple ships fired together, the combined effect created a formidable shield intended to deter incoming threats. However, Japanese aircraft occasionally managed to pass through this defensive barrier. Pilots had developed fast, low-altitude approaches and high-speed dives designed to challenge ship defenses, often coordinating multiple aircraft at once to increase pressure on a fleet. Their goal was to deliver their ordnance as effectively as possible during these high-risk maneuvers. The smaller 20mm and 40mm defensive rounds used by Allied ships required direct hits, which could be difficult to achieve against fast-moving aircraft. Larger 5-inch naval guns, on the other hand, could be used with timed fuses, similar to the German anti-air systems, where ship radar provided targeting data and the fire control system calculated when the shell should detonate near an incoming aircraft. A new challenge arose when Japanese pilots began using more unpredictable flight paths, making it harder for timed fuses to detonate at the optimal moment. This pushed Allied forces to continue improving their defensive technology throughout the conflict. Pilots often shifted altitude quickly, causing defensive shells to pass above or below their aircraft before detonating. A 5-inch shell weighed roughly 55 pounds and could cause serious damage if it exploded near multiple aircraft, but getting it to burst at the correct height was extremely difficult. As a result, ships sometimes needed to fire large numbers of shells just to achieve a single effective burst. Then came a breakthrough that completely transformed these same guns into far more effective defensive tools. This innovation dramatically increased the accuracy of anti-aircraft fire, and later, even standard field artillery, so quickly that opposing forces struggled to understand how it was happening. The idea behind this advancement began in Britain early in the war. Engineers hoped to place a small sensing device in the nose of a shell that would cause it to detonate automatically when it approached a target. With such a design, crews wouldn't need to rely on complex timing calculations or manually adjusted fuses. By 1940, British teams had outlined a workable concept using miniature radio components and passed the design to the United States for further development. American engineers immediately recognized the potential and treated the project with strict secrecy, beginning intensive efforts to refine the technology. The challenge wasn't the concept, it was making the device operate inside a fired shell. Artillery rounds experienced forces of more than 20,000 Gs during launch, and the spin created by rifling added even more stress. The fuse had to survive all of this while containing extremely delicate components: a miniature radio transmitter and receiver, signal detector, amplifier, trigger mechanism, power source, and multiple safety systems. And all of this needed to fit into just a few inches of space at the tip of the shell. Despite the immense difficulty, engineers continued pushing forward, working to create a rugged, reliable system that could function under the harshest conditions of wartime use. Launching a shell placed enormous stress on any internal electronics, so engineers first had to figure out how to protect the device. They strengthened it using small vacuum tubes, and then secured the entire assembly in resin or wax so the components wouldn't shift during the intense acceleration and spin that occurred when the round was fired. Next, they had to ensure the fuse would activate only when approaching an aircraft, not when near the ship that launched it, the surface of the ocean, or other nearby objects. During early testing, the system was so sensitive that it could even react to birds flying close to the trajectory of a test round, showing just how responsive the technology was. After extensive refinement and countless trial and error adjustments, the design finally became reliable. By mid-1942, at a critical point in the war, testing revealed that these new fuses were more than 50% more effective than traditional timed fuses. Production began immediately, and Frontline units received the new technology as quickly as factories could deliver it. Because 20mm and 40mm shells were too small to hold the device, the first recipients were the larger 5-inch naval guns and other medium to heavy anti-aircraft weapons. The new system was given a code name, variable time, or VT, to conceal its true purpose. A full technical breakdown would be extremely complex, so instead, here's the simplified version. The fuse used miniature radio components to sense when the shell was getting close to a target, triggering detonation at the ideal moment. This breakthrough dramatically increased accuracy and effectiveness, marking a major turning point in defensive technology during the war. The new fuse functioned as a miniature radar system powered by a small internal battery that activated only after the shell was fired. Traditional batteries couldn't be stored for long periods without risk of corrosion, so engineers created a tiny sealed glass ampule inside the fuse. This ampule held the electrolyte for a wet battery and stayed separated from the electrodes until the moment of launch. When the shell was fired, the enormous force shattered the ampule, releasing the fluid and instantly activating the battery. Once powered, the fuse emitted a continuous radio signal throughout the shell's flight. As the shell approached an aircraft, the returning signal changed in a measurable way, and when it reached a preset threshold, the fuse triggered the shell to detonate at an optimal distance. Multiple safety features ensured the fuse would only arm after being fired and after traveling a safe distance, preventing accidental activation near the launching vessel. If the shell did not approach any target, it was designed to self-detonate after a short period. This was an important safeguard, as the Allies wanted to prevent any possibility of the technology being recovered and studied by opposing forces, because the proximity fuse was so valuable and extremely secret, on a level comparable to other major wartime innovations. It was initially used only over water, where unexploded rounds would sink and remain unrecoverable. On January 5, 1943, the U.S. Navy cruiser USS Helena became the first to use proximity-fused shells in combat, successfully intercepting an incoming Japanese aircraft. As more ships received these upgraded shells for their 5-inch guns, their defensive effectiveness increased dramatically, surprising opposing pilots who were not expecting such a rapid improvement in accuracy. With this new technology, the number of shells needed to bring down a single aircraft dropped dramatically, from several thousand to roughly 150. The British soon adopted the system as well, using it in their coastal anti-aircraft defenses during raids and against incoming V-1 flying bombs. Their accuracy increased sharply, with reports showing major improvements in interception rates. Any aircraft approaching the English Channel faced far more effective defensive fire than before. Because of concerns that unexploded rounds might be recovered and studied, strict rules limited how proximity fuses could be used. This restriction remained in place until late 1944, when General Eisenhower strongly advocated for their use on land. Approval finally came, just as German forces launched a major winter offensive, hoping to regain momentum and secure key supplies. As the Battle of the Bulge began, around 200,000 proximity-fused shells were quietly supplied to Allied artillery under coded shipment labels. Their impact on the battlefield was immediate. Earlier in the war, timed fuses were sometimes set to burst above the ground to disperse fragments downward. But this required complex calculations and was difficult to execute accurately. Now, with proximity fuses, artillery could detonate at the ideal height automatically. When opposing troops advanced under the cover of heavy fog, believing low visibility would protect them, these shells activated at just the right moment above open terrain. Even defensive positions such as trenches offered limited protection unless they had substantial overhead cover. This new capability significantly strengthened Allied defenses during one of the most intense phases of the conflict, helping them counter large-scale movements that might otherwise have broken through their lines. German field reports eventually reached their high command, describing with surprise how Allied artillery had suddenly become far more effective. The proximity fuse represented such a major advancement that the United States placed many of the production facilities under strict confidentiality, so manufacturing could be expanded as quickly as possible. By the end of the war, roughly 22 million of these VT fuses had been produced. Because demand was so high, the U.S. even enlisted factories that normally made items like holiday lights and small radio bulbs to help build components for the fuses. Workers were instructed simply to produce the needed parts without being told the sensitive details of what they were for. As a result, decorative light production almost completely stopped during the peak wartime years, making them nearly impossible to find in stores. Opposing intelligence services became aware that something unusual was happening, but they were never able to develop a comparable system. Although they attempted to design their own versions, none reached large-scale production. The built-in self-destruct feature and the Allies' strict rules on how and where the shells were used made it extremely unlikely that an intact fuse could ever be recovered and examined.